class we are going to talk about membranes, and I am going to take 2 classes on membranes because there are different types of membranes, large variety of membranes that are used. They act as filter, they act as separating liquids, they act as separating proteins and so on actually. So, different types of membranes each using different principles of operation. So, what are the different types of membranes, especially the important ones that are used for separation? The simplest ones are the microfiltration and the ultrafiltration. So, they are almost like your normal filter. So, they separate based on the sizes, they are used for purification of aqueous stream, concentration and recovery of valuable products. So, they can separate based on the size, sometimes they can separate based on the molecular weights and so on. Then we come to reverse osmosis. Okay. This is a useful technique if you want to remove the minerals present for making potable water. If you are desalinating seawater, reverse osmosis is the technique that is used. Then we come to dialysis and electrodialysis. They are based on concentration gradient. Okay. And electrodialysis are based on applying electric voltage, and the charged ions move based on the voltage that is applied actually. And dialysis is very common in medical settings where patients who suffer from kidney damage, kidney failure are generally treated with this type of technique so that the salts present in their blood are removed. So, we will talk about that. For separating gases, so if I want to separate gases of various sizes, then we can use membranes. Pervaporation is another technique where we can separate and concentrate liquid mixtures. Suppose you have water and an organic. So, I want to remove the water present, even the minutest amount of water can be removed using this type of technique. Especially this is very useful if you are concentrating fruit juices. We can't really heat fruit juices in a distillation column because they may get charred. So, we can use this type of technique called pervaporation. So, so many different types of membrane based processes, and they all use different principles for their operations. Okay, and we are going to spend some time in each one of them. So, membranes are about 150 micron thick, and of course, you also have thin membranes which are 1 micron thick. If you look at the worldwide consumption of membranes, so it has, although this data is 2001, it keeps increasing and increasing because membranes are used in water treatment, in environmental applications, in separation processes and many industries. So, their usage is going up and up. So, composite membranes, that is reverse osmosis membranes, take up chunk of membranes application. Then comes nanofiltration membrane, ultrafiltration membrane and so on, then the microfiltration membrane. Okay. So, these are the driving forces by which membranes operate. If you look at microfiltration, generally the pressure is of the order of 0.1 to 1 bar, and the pore size is generally 0.0 to 10 micron. And what is the principle? It is based on sieving. That means it is almost like your filter. It captures or retains large particles and allows particles of smaller size. So, that is the microfiltration. Then comes ultrafiltration. Now, you can see the pressure is higher, and the particle membrane pore size also has come down. So, it has gone down to 0.001 to 0.02. Again, this is also based on sieving. So, I can capture smaller particles, I can also capture molecules of different molecular weights using this, but of course, the pressure is high. Then comes you have the nanofiltration, that is still smaller, and then comes reverse osmosis, and we are applying a very large pressure, almost 100 bar pressure. There are no holes here, okay, absolutely no pores here, and the technique or the mechanism is diffusion based here. Then comes dialysis. As I said, this is used quite a lot in medical settings. It is based on the concentration difference. So, you have very high salt concentration in the blood, which whereas on the other side you have the dialysate which has very little salt. So, because of the concentration difference, there is a flow of salt from high concentration to low concentration. Okay. The pore size is quite small, okay, in nanoscale actually. So, it is more of a diffusion based, although here it is mentioned as sieving, it is more of diffusion based. Then you have the electrodialysis, you are applying an electrical potential. So, the separation is based on the electrical potential. We can go down to molecular weight less than 200, and the principle is based on ion migration. The ions get moves or migrates based on the electrical charge. Okay. Then comes what are the applications of this membrane separation process. Suppose I have inorganic salts and I want to separate, okay, sodium chloride, potassium chloride and so on, then I use reverse osmosis type of membrane. If I have simple organic substances like acids and sugars, okay, of slightly higher molecular weight, you can go to nanofiltration or we can go to reverse osmosis. Antibiotics, although I have put reverse osmosis, we can even go to microfiltration, nanofiltration, and then of course reverse osmosis. So, if you have large material like proteins, enzymes, we can go up to ultrafiltration. So, you see very small size reverse osmosis, and as we keep going up we may be able to go up with the nano, micro and even ultrafiltration. Okay. So, if you have viruses which are about 30 to 300 nanometer size, we can go up to ultrafiltration. Colloids, okay, they are much bigger in size, we can even go to microfiltration, okay, dialysis. Bacterial cells, they are much bigger, then we can go to ultrafiltration, microfiltration and dialysis. Yeast and fungi which are much bigger, we can go up to microfiltration. So, depending upon the type of material, metabolite, a polymer, a biopolymer, a bacterial cell, a virus cell, a biomaterial or a biological molecule, we can use membranes of any type. There are huge number of membranes available, and that is the beauty of membrane technology. So, reverse osmosis and nanofiltration membranes are made up of generally cellulose acetate, ultrafiltration membranes are made up of ceramics, polysulfone, polyvinylidene difluoride PVDF, polyvinylidene difluoride and cellulose acetate. So, we can see hydrophobic, hydrophilic. So, we can have a wide range of products that could be filtered using ultrafiltration membranes. If you come to microfiltration, it is made up of ceramic, polypropylene, polysulfone, again PVDF type of material. Okay. Again you can have a hydrophilic and hydrophobic type of material. So, you have a hydrophilic material, we have hydrophobic and hydrophilic material, synthetic, these are synthetic polymers, and these are inorganic material. Again you have some synthetic polymers like PVDF, inorganic material. So, some of these materials can take up very high temperature, some of these materials like cellulose cannot take up very high temperature. Okay. So, we can have a wide range of operations depending upon the material of construction of these membranes. So, operating pressure, you have 15 to 150 bar reverse osmosis, 5 to 35 bar nanofiltration, 1 to 10 bar ultrafiltration, less than 2 bar microfiltration. Pore size, reverse osmosis and nanofiltration very small, 0.002, ultrafiltration 0.2 to 0.02 micron, microfiltration 4 to 0.02 micron. Again that is the order actually, because the pore size is becoming smaller and smaller and smaller, pressure also becomes larger and larger and larger. Okay. Now, maximum operating temperature, as you can see, cellulose acetate we have 35 degrees, PVDF 95 degrees, polystyrene composites 80, and this is about 80 to 90 degree centigrade. So, we can reach almost 100 degree centigrade with synthetic polymers okay, as membrane material. So, basically the membranes technology can be grouped as separation based on equilibrium distribution, separation based on differences in transport rates. Okay. Transport rates happens because of charges, transport rate happens because of concentration gradient and so on actually, or osmotic pressure. Okay. So, these are the principles by which membranes happen. One important point which we need to understand, that is called concentration polarization. So, when I am doing a membrane operation, as the fluid moves in, this is the membrane material, this is downstream. Okay. So, the concentration of the solute keeps building up, and generally the concentration of the solute near the upstream wall is very high, okay, much higher than the bulk. So, as the concentration keeps building up, that is called concentration polarization, the flow keeps going down, and after some time there is no flow at all of the liquid here because of the build up of this solute here. We can develop a small model for this build up of this concentration, and we can calculate what will be the concentration at the surface of the upstream side of the membrane, okay, that is called CS, whereas Cb is the concentration in the bulk. Okay. So, we can use Fick's law, we have a flow of solute in the bulk, and then you have the diffusion here. So, you have a J is the flux, then the concentration is equal to minus d dC by dx. Okay. So, x is the direction. So, at x equal to 0, that means near the wall on the upstream side, concentration is Cs, and at x is equal to d, if we call this as the thickness of a boundary layer, a stagnant boundary layer here, at x is equal to d, concentration is Cb. Okay. So, this is a first order differential equation, simple equation, and we have two boundary conditions, C is equal to Cs at x equal to 0 and x equal to dC is equal to Cb. So, we can solve them and end up with a simple relation, J the flux is equal to capital D, that is the diffusion coefficient, small d is the thickness of the boundary layer, logarithm of Cs divided by Cb. Cs is the concentration of the solute on the upstream side near the membrane wall, Cb is the concentration at the bulk. Okay. Now, d by d, that is capital D by d, is also called mass transfer coefficient, and the units will be distance by time, okay, whereas capital D is called the diffusion coefficient. So, I can calculate if I know the flux, and if I know the diffusion coefficient of the solute, and if I know the small d, that is the thickness of the bilayer, I will be able to calculate what will be Cs, that is the concentration that build up and the upstream side of it. Okay. This is a simple problem. I am carrying out an ultrafiltration process at a rate of say 2.6 into 10 power minus 3 centimeter per second. Okay. The concentration of the solution in the bulk, that is Cb, is 0.44 weight square. Diffusion coefficient is given like this, 9.5 into 10 power minus 7 centimeters per second, and the boundary layer is about 180 into 10 power minus 6 centimeter, that means 180 microns. Okay. What will be the concentration of that surface, that is Cs. I just use that equation, okay. J is equal to capital D by small d logarithm, okay, Cs by Cb. So, capital D is given here 9.5 into 10 power minus 7, small d is given 180 micron, okay. The flux is given on this left hand side. So, from there I can calculate what is the Cs by Cb ratio, it is coming out to 1.63. That means concentration at the wall on the upstream side will be 63% of the bulk. Okay. So, whatever be the bulk concentration, there is a build up of almost 63%. So, as you keep on doing the membrane process, the build up will keep on happening and the rate will keep on decreasing actually. That is a big problem with this type of process actually. Okay. So, you use this equation, of course, quite a simple equation and quite a simple problem, but it gives you some idea about the entire process. Now, what are the factors that affect the separation? Concentration polarization is a big problem, and it is reversible. We can always flush the membrane surface on the upstream, so that whatever has built up can be removed. Fouling of the membrane, this is a very long term problem, and sometimes it is irreversible, because the whole membrane surface there could be a bacterial contamination, biofilm formation and so on actually. So, fouling is a big problem, whereas concentration polarization can be overcome because it is a reversible process. We can do a back flushing or cross flow type of approach to remove that. Okay. So, what are the fouling? The flux through the membrane decreases slowly with time because of slime formation, microbial growth, deposition of macromolecules, especially in ultrafiltration. If you have large molecules, they will start depositing, colloidal deposition, sometimes physical compaction, especially RO membranes. We are talking about 150 bar. So, what happens is the whole membrane could get compact. So, the flow becomes big problem and finally it may stop. So, all these are problems which are an issue in membrane technology. So, there are some ways of overcoming these problems, and after some time you may have to throw the membrane and buy a new one. So, that is operating cost. So, cost of the membrane becomes the operating cost. Okay, so, fouling is irreversible. So, you have to ultimately replace. It can be inhibited. That means it can be slowed down by using hydrophilic surfaces, because they are less prone for fouling, by proteins. Pre-treatment of the feed. So, we can pre-treat the feed so that fouling does not happen. We can adjust pH initially so that some salts that are present in dissolved form can precipitate out. So, we remove the precipitates and then we can carry out the membrane process. Frequently we have to clean the membrane with chemicals. Back flushing. So, you flush backwards so that whatever if there is a concentration polarization or fouling, that gets dislodged and removed. So, cleaning techniques, forward flushing, backward flushing, air flushing, chemical cleaning, all these are different ways, methods that are followed to clean your membrane. So, how do we decrease or prevent fouling? We can add biocides. So, there are chemicals which will prevent biofilm formation and biofouling. We can change the pH so that salts do not precipitate out, okay. So, that will prevent the scaling. We can also have a pre-filter, that means you can have a small microfiltration system which can remove suspended solids, and then we can adjust the pH. Once there is a settling of some dissolved solids, again we can have another pre-filter. So, all these are ways of preventing fouling in a membrane system, and especially for RO membranes, they are very costly. So, we do not want scaling and we do not want fouling. So, we may end up having a couple of pre-filters in the early stages actually. So, we may add a pH adjustment, filter, then we may add biocides and then go to a RO membrane setup. So, these are called pre-treatments. So, if you have dissolved solids there is no problem, but suspended solids or if solids precipitate during the process, then that is a problem. So, prior to membrane filtration, we can have another filter to remove suspended solids, oxidizers and precipitates. So, we can initially adjust the pH and then dissolved solids may precipitate out, and again we can have a settling tank or a filtration, and then you can have a pre-filter to prevent plugging. Then we can add biocides or fungicide to prevent bacterial growth. So, like I said, so we can do so many things before they actually go into the membrane, which is very expensive. So, we can have different types of membranes early which are cheaper, and then go to membranes which are more expensive. So, typically this is how it looks. You have a pump and it goes, you have the membrane module, then we get the filtrate, okay, and then this is where the membrane is placed. So, this is a direct flow, directly hits and then the filtrate comes out. So, analogously we can also have cross flow. I will show you that picture also, okay, or like we have dead end filtration and cross flow filtration, same way we can have in membranes also. So, how do you increase the velocity at the membrane surface? We can create turbulence, we can decrease the thickness of the concentration boundary layer, we can also delay the onset of concentration polarization. All these can increase the velocity of the membrane surface, and thereby it can also enhance the entire process, that means the separation process. This is a cross flow filtration. If you remember analogous to the dead end, this is a cross flow filtration. So, here your solution flows parallel. So, obviously there is not going to be a concentration polarization and there is not going to be a scaling also formed here actually. Okay, so that is the advantage of this type of design. Just like your filter, if you remember a few classes back we talked about cross flow filtration. So, here also we can do that. So, a typical equipment will look like that. You have a feed tank and then you take through a pump, have a cross flow permeate. This is called a permeate, okay, and then the other one is called the retentate. Whatever that does not pass through the membrane is called retentate, and whatever passes through the membrane is called permeate. So, we can keep doing this many times until the solution here in the feed tank becomes very concentrated. Okay. So, what are the design criteria? A high membrane surface to volume ratio, this will minimize the space requirement and capital cost. So, we can have a very high membrane surface, but of course, when I use lot of membrane, I am going to spend some money on the membrane cost. So, you have to remember that equipment may be smaller, but the membrane cost will go up. So, you need to balance that. Adequate structural support, so that the membrane even thin membranes can withstand very high pressures. A low pressure drop on the concentrate side. So, we have enough driving force for permeation. Turbulence in the upstream side, so that there is no concentration polarization and minimize fouling. Provision for back flushing, okay, so that whatever scales that are formed can be removed, and then also we should have option to replace the membrane. Whatever you do, the membrane life is fixed, and after some time we need to replace the membrane. It could be weeks, it could be months, it could be years. So, whenever you replace the membrane, you are adding to the operating cost. So, you need to remember that. Okay. Different types of membranes that are available: the flat sheet membrane or plate and frame, spiral wound membrane, it is in the form of spiral, tubular membrane, it is in the form of tube, hollow fiber module, that is shell and tube type of membrane. So, these are some pictures of it, right. So, this is a tubular membrane. So, this is a tube and this is a porous membrane. So, your slurry is flowing like this, and you get the retentate here, and then on the along the circumference you get the permeate. The plate and frame type, it is like a plate and frame, you have the membrane material in the middle. So, the slurry flows and then you get the permeate here. Third type is shell and tube. So, almost like a heat exchanger, we have lots of tubes which are made up of membrane material, so sort of porous. So, the permeate comes out on the shell side, the retentate comes through the tube side. So, you introduce the slurry here, many tubes are there almost like heat exchanger, and then the retentate comes out here, and then the permeate comes out through the shell side. Okay. So, these are the various designs. Then you have the spiral wound type also, it is like a spiral. So, there are different designs, and as I showed, there are different materials of constructions also that are available for making these membranes. Osmotic, reverse osmosis is a very important type of membrane process, which is used quite a lot for desalinating seawater, for making potable water and so on actually. So, we need to little bit understand what is osmotic effect and what is osmotic pressure, hence we can understand what is reverse osmosis. So, if you take solvent molecules, they pass from a region of lower concentration, okay, to a region of higher concentration, okay. Lower concentration of some solute to a region of higher concentration of a solute. So, the driving force for the flow of solvent is chemical potential, okay. So, you are trying to balance the chemical potential. So, when the concentration of a solution is low, the chemical potential is high, and the concentration of the solute is high, chemical potential is low, and so from a low concentration the solvent flows to a higher concentration, and then there is a balance. This is called osmosis. So, at equilibrium the chemical potential on both sides of the membrane are equal, and the fluid pressure is called the osmotic pressure of this solution. Okay. So, let us look at this pictorially. So, suppose I have brine, salt, brine is nothing but salt solution. I have pure water. Okay. So, what is happening? Brine you have salt. So, obviously, there will be certain pressure, chemical potential, and you have pure water. So, there will be certain pressure. Okay. And the chemical potential for the water side, chemical potential for the brine side. So, this chemical potential is higher than this chemical potential. So, pure water will start flowing inside across this membrane into this, okay, until these two chemical potentials match. So, if in order to overcome that, if you this is called osmotic pressure. Okay. Now, in order to overcome that, I need to apply certain pressure so that they do both balance. That is called reverse osmosis. Okay. That is reverse osmosis. Okay. So, we have pure water here on this side and salt solution on this side. So, because there is a salt solution, the chemical potential is low. Because it is pure water, chemical potential is high. So, the chemical potential has to be balanced. So, pure water will flow into this and until it balances, and that is called the osmotic pressure. Okay. And if you want to balance these, you apply some pressure so that they get balanced, and that applied pressure is called the reverse osmotic pressure. Okay. And that is what happens in reverse osmosis process. Okay. In the reverse osmosis, when I apply certain pressure, the solvent here alone will flow, the salt or the inorganics present will not be able to flow. Okay. So, I can concentrate this side more and more of salt, and I can collect more and more of the pure solvent. That is what happens in reverse osmosis. So, if I have the seawater and I apply that pressure, osmotic pressure in the form of reverse, that is reverse osmotic pressure, water alone will flow through the membrane and this side will become more concentrated brine. Okay. So, let us look at some equations. The permeate flux is J is equal to L into delta P. L is called the membrane permeability and delta P is the pressure, that delta P is the driving force. Okay. So, but osmotic pressure will also play a very important role. So, that will be sort of having a negative effect, or it will decrease the driving force. Okay. So, J is equal to L delta P minus S POS. POS is the osmotic pressure given by, if you remember, Van 't Hoff's relation nRTC, RT gas constant, temperature and concentration of the salt. S, if S is equal to 0, okay, that means the solids are completely passed. S is equal to 1, the solids are completely retained, or the solids do not pass through the membrane material. So, if the solids do not pass through the membrane material, you have on the upstream the concentrated solution with the solids, and you have on the downstream only the pure solvent. So, osmotic pressure will be fully acting, whereas if the solids completely pass, you have on both the sides solution containing solids. So, there will not be any osmotic pressure acting. So, S will become 0. So, this is the equation which we can use, and L is the permeability, and generally a manufacturer who is a supplier of the membrane will give you this L value to you. Okay. So, if I know the L value from the manufacturer, I can calculate what will be the flux through the membrane. So, let us look at each one of these types of membrane as we go along. Okay. In the next class as well. As I said, we have the starting from microfiltration, we go to ultrafiltration, we go to nanofiltration, we go to reverse osmosis and so on actually. So, in reverse osmosis, the membrane pore size is very, very small, okay, practically 0, and the flow happens, okay, flow happens, that means the solvent flows through the membrane material, and salts and low molecular weight materials are retained. Okay. So, in the normal osmotic pressure, as I mentioned before, the solvent diffuses through the membrane from the solvent side to the solution side. In reverse osmosis, what we are doing is we are applying very large pressure, so that the solvent flows from the solution side to the pure solvent side. Okay. That is what happens. If you remember this, it flows from the solution side to the pure solvent side. That is what it does in reverse osmosis. So, we can use it for separating low molecular weight products such as salts, desalination of seawater, sugars, organic acids from aqueous solutions. It is used quite a lot in food and dairy industries to concentrate fruit juices. That means I can just remove whatever water is present, little amount of water present in my fruit juice. We can use it for vegetable juices. So, I can operate it at room temperature, I do not have to heat up the fruit juice to remove the water. Okay. So, that is the advantage of reverse osmosis, but the running cost is high. The reverse osmosis membrane cost is very high, and then comes the nanofiltration. This is almost like reverse osmosis, but the membranes are slightly more porous. So, we can use it for separating molecules up to 500 Dalton. You can see here it is very small, and here we can reach for up to 500 Dalton actually. Okay. So, we will continue these membranes in the next class also. Thank you very much.